For the second half of Chapter 4, we're going to look at contingency tables and conditional probabilities. Contingency tables allow us to visualize bivariate data. So we've been working so far with univariate data. This is data that is from one variable of a population. Bivariate data is when you have two variables from the same population. So I'm going to show you a very basic contingency table. The two variables, one of them is age, and the other one is rank of faculty members at a university. So when you look at this contingency table, notice we have a total of 1,164 faculty members. Let's look at rank first. There are 4 different ranks, noted by R1, full professor, R2, associate, R3, assistant, and R4, instructor. So of that 1,164 faculty members, 430 are full professor, 381 are associate, 320 assistant, and 33 are instructor. But we've also are looking at the faculty members' age. 68 are under 30, 402 are between 30 and 39, 348 are in their 40s, 253 in their 50s, and 93 are 60 and over. But each faculty member has a rank and an age. So for example, of the 430 that are full professor, 2 of them are under 30. 52 are 30 to 39, and so on. We can see that there are no faculty members, ages 60 and over, of the instructor rank. Instructor's the lowest rank. That's the rank most faculty are hired at. So this is a basic contingency table. A couple things I do want you to note. The rows add up. This represents the total for each row. The numbers across the bottom represent the total for each column. The column totals and the row totals both should come out to 1,164. Also, each of these individual cells, the 20 inside the bold box, should also equal 1,164. Now, this is a basic contingency table. We're going to turn it into a joint probability distribution by taking the information and turning it into a probability. And the way we did this, quite honestly, is simply we took each individual number, so the 2 full professors who are also under age 30, divided it by the total, 1,164. So basically, we're doing our F over N for each cell, the cells in the margins and the cells within the bold box. And here we have a joint probability distribution. The numbers outside the box, which represent, remember, those column and row totals, they are called our marginal probabilities. Down here too. Quite simply because they're in the margins. The numbers inside the box, the 20 probabilities on the inside, are your joint probabilities. So now we know that a faculty member selected at random, the probability that that faculty member is an associate professor, age 40 to 49, we just need to follow the table, equals 0.107. So there's a 10% chance that a faculty member selected at random at the institution is an associate professor age in their 40s. So this section is just going to allow you to work with these joint probability. Okay, so for some of the things you're going to do in this section is basically just answer some questions related to the contingency tables. And then one of the things is if you are given a contingency table, so I went back to this one and just kind of blacked out some of the numbers, is you're going to have to fill in the missing information. And you can do this just by understanding, finding, getting the row totals and subtracting. I think it's pretty intuitive. For example, you wouldn't start with this particular row that has 2 missing features because that's not going to be very helpful to you. You might start looking this way first and doing this number, and then doing this number, knowing the total should be 430, subtract what's given, and you can find what's left over. And as you start to populate, you won't be able to get the total, of course, until you get the other totals. So as you start to figure out through subtraction of the totals, you can fill in then eventually all of the pieces of your contingency table. So now the contingency tables set us up. So again, don't forget, you are going to be working with both the probability, the actual contingency tables with the numbers in them, and then the probability distributions, where the numbers are turned into probabilities. And we're going to finish this chapter 4 on conditional probabilities. So by definition, the probability that event B occurs given that event A occurs is called a condition. We're placing a condition on our event now. And it is denoted by, this is red, the probability of B given A. And we call A the given event. It's also called the condition. So let's talk about this 1 second with something we're familiar with, which is a deck of cards. We know we can take the probability of a king, right, in a deck of cards. Well, it's 4 out of 52, which is 1 out of 13, which of course reduces to 0.0769. But what if I place a condition on that probability? And now I want to know, what's the probability of a king given that you have a face card? Now, this probability may or may not change with this condition, and we'll talk a little bit about that later, which gets into whether events are independent or dependent. But what the condition ultimately does is it changes your sample space. You are no longer working with that entire deck of 52 cards. So you no longer have 52 as your denominator. Now, we have changed it's kind of like you've gotten rid of every card in the deck and only kept the face cards. So how many face cards are in a deck of cards? Well, there's 3 in each suit, 4 suits, so that's 12 face cards. When you place a condition on a probability, remember, your sample space changes. Your capital N changes. Of those 12, how many are kings? Well, of course, there's 4. We still have 4 kings, but we're no longer 4 out of 52. Now we're only 4 out of 12, which of course is 1/3, and that's a much higher probability than just selecting a king. So that kind of gives you this idea of, I wanted you to understand conditional probability before you see the formula for it. Now we're going to go through the same problem, but let's look at the formula for conditional probability. So the conditional probability rule states that for any 2 events, A and B, the probability of event B given event A has occurred equals probability of A and B together divided by that condition, in this, which would be, according to this formula, probability of A. So how does that look with our king given that we have a face card? So first of all, if you're going to try to follow the formula, identify what is your probability of B and what is your event A. okay, which may have been different than what you came up with before, but in this case, B is the probability we're trying to find, and A is our condition. So then I rewrote the formula using king for probability B and face card for probability A. So I have probability of king and face card divided by the probability of the face card. So using the formula, let's go through the probability. So king and face card. So what's the probability of getting a card that is both a king and a face card? Well, there are 4 cards that have this attribute, right? So it's 4 out of 52. And then divided by the probability of just getting a face card. So how many face cards are there in a deck of cards? We've already stated there are 12. So that's 12 out of 52. And if you remember how to work with fractions, you can multiply both denominator and numerator by that denominator of 52 to remove it. So we could do 52 over 52, remove that. Or you can just use your calculator and get the decimals for each and divide them however you want to do it. Either way, you're still going to get 4/12, which is 1/3, which is 0.333. So whether you do it intuitively or you actually use the formula, you're still going to get the same probability. So now, let's move on to our joint probability table. Here we have a joint probability distribution of marital status and gender. So we have males and females. Using the same percents in a problem we did last time, females represent the year this particular book was written. Females represented 51.6% of the population and males represented 48.4% of the population. So there's our probability total for males and females. And then, of course, we have the number of people that are singled, the number of people that are married, widowed, and divorced. So the first one I want to calculate is what is the probability that an adult selected is divorced, so that's M4, given that the adult selected is male. Male is S1. So the probability that they are divorced given that they are male. So again, go back to your formula and rewrite it using the probability formula. So here's the thing. When you actually have the full numbers, the contingency tables of the actual totals, it's a lot easier to do it intuitively, but when you have the probabilities themselves like we do in this table, you really need to revert to that formula to make sure you're doing it correct. So here we have, well, this would be the probability of S1 and M4 divided by, remember, you are always dividing by the condition. And the condition this time is S1. And that's one of the things you need to remember all along is what do you divide by? And it's always the number that comes after the bar. It's always the condition. So the probability of male and divorced, well, we just got to find that. Here it is. Male, divorce, probability is 0.044. And then the probability of that condition of being male, so the probability of S1 is the total. So there it is, probability of S1. So we divide it by 0.484. And you get 0.091. And that's your conditional probability. So let's take a look at another one. Hit pause, and I want you to calculate what's the probability that an adult selected is male, given that the adult is divorced. So I'm changing the probability. Do you see that? Now the condition is reversed. For the one before, we did what's the probability that they are divorced given they're male. Now I want you to find the probability that they're male given divorced. So take a minute, hit pause, find that probability. Okay, so Obviously, though, our denominator, whether you have S1 and M4, M4 and S1, notice the denominator the numerator, sorry about that. The numerator stays the same. That probability still comes from the cell of 0.044. That probability stays the same. What changes is our condition. And our condition here of probability of divorced is 0.104, which leads this to a much greater probability. So there's a greater chance of selecting a male given that the adult is divorced than there is selecting someone divorced given that they are male. So this is important for you to understand that you cannot simply switch the condition and the probability and try and get the same answer. That's not going to happen. Now, let's talk about the general, we're moving into the last section here, 4.6, the general multiplication rule. So now we have A and B represent any two events. Probability of A and B happening is the probability of A happening times the probability of B, but we can't stop there because it's not just the probability of B for our second event. It's the probability of B given that A already happened. So the easiest way to kind of understand this particular multiplication rule is, and now let's talk about selecting two cards from a deck of cards without replacement, meaning after I select the first card, I'm not going to go put it back. Okay, so here, again, we want the probability of selecting a face card given that we select a king first. Recall, in this problem, we are actually taking two cards out of the deck. So, probability of selecting a face card given that there's already a king gone, and that king is a face card. So normally there are 12 face cards in a deck of cards. 3 in each suit. 3 times 4 is 12. But since we know there's a king missing, we have 11 face cards, because we're given that that king was already taken out. Our normal 52 deck of cards is down to 51. So when you take 11 divided by 51, get about 2.16. So for the probability of A and B, of them both occurring, meaning we select a king, then we select a face card, we would first have the probability of A happening. A is just selecting a king. There are 4 kings out of 52 cards. So you can multiply that. We've already calculated what the probability of B given A is, or you can just write the fraction again, 11 out of 51, or multiply it by the 0.216. So 4 divided by 52 is 0.0769 times 0.216, and it looks like we get 0.017. Already taken out of the deck. So let's think about that without using our conditional probability. So now let's do this concept and try to understand this concept of independent events. B is independent of A if the probability of B selecting A actually equals the probability of B. So if that condition had no impact on our original probability, then those two events are considered independent events. So let's go back to, and again, you got to read the problems carefully. We're going to go back to just selecting one card from a deck. All right? We want to know if selecting a king is independent of selecting a face card. So let's try it. In order to figure that out, first of all, we need to know the probability of selecting that king. Well, that's easy again. 4 out of 52. We've done this a bunch of times. So that's our probability of selecting a king. Well, now, for A, we need the probability of selecting a king given that we know there's a face card. Well, I think we did this one a little bit earlier as well. If we're only looking at the face cards, well, there's only 12 face cards, and the probability of getting one of those 4 kings out of 12 face cards is 0.333. So here, is K independent of F? Well, we would just need to look at those probabilities. Does the probability of K equal the probability of K given F? No. Okay, they are not independent, or they are definitely dependent events. Let's take a look at B. Well, we already know the probability of K, so let's take a look at the probability of K given H. What's the probability of the king given you know you have a heart? Remember, we're going to limit our sample space now down to just hearts. Only going to look at hearts. How many hearts are in a deck of cards? Well, there are 13 of them. And of those 13 hearts, how many are kings? Just 1. So we have 1 out of 13, 0.077. Please notice that 0.077 is also the probability of just K. So, king is independent of hearts, but it is not independent of a face card. And simply think of it proportionally. If you draw a king from a deck of cards, right, it's 4 out of 52, which reduces to 1 out of 13. If you limit that deck of cards to just one suit and you draw a king, it's the same probability, right? Proportionally, it's the same because it's the 1 out of 13. But if we limit it to face cards, our proportion then changes. So that's why the one is independent and the other is not. So this concludes our videos for Chapter 4. Thank you.